So the first piece of relativity that we're going to see that will probably really bother you is if we decide to put a clock on our train, and everything's done on a train because when relativity was invented in 1905, when Einstein figured it out, everybody traveled by train. So let's put a clock on this train and let's make it the simplest clock we can imagine. No gears or electronic circuits or anything like that. We just have a vertical pair of mirrors, so one right above the other, and light just bounces back and forth between them, and it takes a certain fixed time to do that. If we wanted one round trip to take a second, then these two mirrors would have to be 150,000 kilometers apart from each other, so that's probably a little bit much, but again, in principle, it doesn't matter. Uh, each tick for you on the train, the time will be 2d divided by speed of light, where d is the distance between the mirrors. If, for example, d is about 6 inches, then each tick would be a nanosecond. Now, what if somebody on the train station watches you go by with your clock? Of course, you're going to be going by at high speed. What they would see, instead of the light just going vertically up and down, they'd see the light leave this lower mirror here on the left, but when it got up to the higher mirror would have moved over a lot. The light bounces off and it goes back down to hit the lower mirror again, by which point the lower mirror has moved a lot. If we do the math here, what this person is going to say is these distances s for these things. So 2s is a much longer distance than 2d. You just say it traveled 2d. This person is going to say it traveled 2s, which is much longer. We've already established that everybody will agree on the speed of light. So the only way this person can make sense of this very long trip, of light taking this very long trip, is to say, well, this clock is slow. You said it takes 1 nanosecond to make a tick. This person may see this trip take 3 nanoseconds. So the only way they can reconcile that in their heads is to say time is moving slower on this train. And that sounds crazy. The math that we get out of this would be our vertical distance is still 2d. The horizontal distance now, left to right, is L equals V delta T over 2. And the distance traveled by the light, the S, is this, 2 squared of L squared plus D squared. That has to be covered in time delta T. So what we get is this is the connection between the time on the train, delta tau, and the time according to the person watching from the track. So this difference here, 1 over square root of 1 minus V over C squared. Sounds complicated, but it doesn't look that bad when you look at it. This factor comes up so often we call it gamma. We give it its own symbol, and we'll use this a lot. This basically tells you how relativistic is a problem. Now, when we say that the train clock is slow, that's not the same meaning that you hear in everyday English when someone says a clock is slow. If they say a clock is slow, what they mean is it's set back by a few minutes. You just need to pull it down off the wall, adjust the hands, and it'll be okay. This clock is not behind. It's literally slow. If you had a clock like this, you would throw it out because you'd say every day I have to reset it by so many minutes. So the point of making a clock this simple is this time dilation effect, as it's called, is not some kind of weird mechanical stretching of the gears or anything crazy like that. It's time itself that slows down. Whatever way you can think of to measure time, however you measure it, you'll see that the people on the train don't get the same value as the people on the platform. Now, if that's not bad enough, let's say the person on the platform bought the same kind of clock you did and it's standing beside him. When you and the train go by her clock at the station, you'll see the light pulse from her clock take the same path, backwards of course, but you'll say that thing is not going straight up and down. You'll get that the train station clock is exactly as slow as they say yours is. And the reason you at least get the same number there is one thing you agree on is your relative velocity. People on the train will say, "Oh, the train station went by me at negative 80% the speed of light." People on the train station will say, "No, the train went by us at positive 80% of the speed of light." And it's okay because in relativity, you could always claim the other person is the one moving and you're at rest. So when you look at anybody who has a velocity relative to you say their clock and therefore their time is running slow. In special relativity, you would never say someone else's clock is running faster than yours. So next we're going to see what that implies.